Hi folks, welcome back to a discussion on the Solaris 11 operating system. I hope you've had a chance to look at the installation of Solaris 11 using live media, installation of Solaris 11 using text ISO image, as well as administering packages in Solaris 11 using image packaging system, also known as IPS, and of course the service management facility to manage services in Solaris OS. In this segment, I intend to walk you through the ZFS file system in Solaris 11 in somewhat detail. We did make a passing mention about the ZFS file system when we discussed the package administration episode. In the package administration, we spoke about a command called the BEADM command, the Boot Environment Administration command. And ZFS, being the mandatory root file system in Solaris 11, gave us a lot of convenience of a risk-free upgrade because of its features like snapshots, for example. So we looked at the BEADM command, understood that it was possible to create a snapshot of the root file system which consumed negligible amount of space, perform the upgrade on that snapshot, and revert back to the original file system in the event something went wrong. So it was a risk-free upgrade that we talked about in package administration, thanks largely to the ZFS as a mandatory root file system in Solaris 11. ZFS as a file system made its way into Solaris in the 6/06 release of Solaris 10 operating system. Of course, it's now 10 years since ZFS has made its way to Solaris OS, so one can imagine the amount of improvements and additions that these file systems have had. So in this segment, I hope to walk you through some of those basic commands in ZFS and some of the basic features that the ZFS file system offers you in Solaris 11 OS. Now, before I take you to the specific commands to administer ZFS in Solaris 11, I want you to please take a look at my S11 desktop virtual machine in VirtualBox. If I go to the settings and to the storage of this virtual machine, there are 6 additional hard disks that I've added to this virtual machine, each of 1 GB size. Now these hard disks are added specifically for the demonstration of the ZFS file system. We only had 1 hard disk to start with on this virtual machine, which is where our operating system is installed. That's around 16 GB of space. You will remember doing this during the live media installation. The rest of the 6 hard disks that you get to see here was added after that, specifically for demonstrating the ZFS file system. Because the virtual machine is running now, you're not able to see the option to add these hard disks. But if I had halted this virtual machine, you would have seen an option on the screen to add additional hard disks onto your virtual machine. So if ever you feel like playing around with the ZFS file system, make sure you leave the boot disk aside and add additional hard disks onto your virtual machine to play around with it. It's not difficult affair to do that. My system is up and running here, and I can run the command echo format to list the hard disks that I have. Like I mentioned, there are 6 additional hard disks. Of course, what you see on the output, there are 7 in numbers, but the first one, of course, is the boot disk. We're going to play around with the hard disks starting from C1 T2 D0 all the way till C1 T7 D0. That's what we would be using for performing administrative activities on ZFS file system. Before I show you the commands, one of the things you might want to keep in mind is that the first job that you do, the first task that you do to use the ZFS file system is to create a pool. Pool of what? Pool of devices. I'm very careful about not using the word disk here. Instead, I used a word called device because that device need not be a disk. It could be a disk, it could be a partition of a disk, it could be a large file also. Of course, large file is something that you probably won't see in production, but that's a possibility to be a participant in the pool. So again, ZFS starts with the creation of a pool of devices. That device could be a partition of the hard disk, a full hard disk, or a large file that you create using the mkfs command, mkfile command, sorry. So I'm going to create a pool with those 6 disks that exist. Of course, I'm not going to use all the 6 disks at a single stroke. We would probably be playing around with some of the commands in a ZFS file system, so we'll have to reserve a few of disks for later purpose. But that's what we do first. We create a pool called ZFS Pool to start with. You would remember traditionally when you wanted to make a file system accessible to the users, to its consumers, you had to partition the hard disk, you had to create a file system on top of that partition, you had to mount that partition in the empty directory or a mount point, and then you had to make an entry in a file called etc/vfs tab so that the file system automatically mounts during the booting process. The good news is that if you embrace ZFS as the file system for your Solaris 11 OS, you don't need to worry about any of this. In one stroke, in one command, you're able to create a file system, mount the file system, and the file system is going to mount. The mount of the file system is going to persist across the reboot as well. Let's create a pool. One more time, I'm going to list the disks that we have. We will not, of course, touch C1, T0, D0. We're going to use C1, T2, D0, C1, T3, D0. So let's create a pool. Zpool create. Name of the pool is my pool, and that's C1, T2, T0, C1, T3, T0. I think the command is self-explanatory there. I'm going to create a pool. Pool of what? Pool of devices. In this case, pool of 2 disks. One is C1, T2, D0. The other one is C1, T3, D0. Now, before I run this command, maybe it is worth looking at the file systems that are currently mounted. You know, there are, of course, you can leave aside this particular file system. This is the Solaris 11 live media DVD that I have mounted on this virtual machine, so not to be considered. But otherwise, if you see, all of these file systems are actually created on a pool called R pool, which is actually the root pool. So I think we're kind of getting an idea. Once we create a pool, we probably create file systems on top of that pool. That's what we might be ending up doing. But for now, keep in mind there is only one pool, and that is our pool. Something we can also list by using the zpool list command. The zpool list command is also showing me there is only one pool, and that pool has a name R pool and is of size approximately 16 GB. And in the same output, I can see how much amount of that is free, etc. All right, so I have it with me. I have only one pool, R pool. Now is the time to create the pool. Zpool create. Name of the pool is my pool, C1, T2, D0, C1, T3, D0. Let's see what happens. Of course, a pool is created, which is what the message says. My pool successfully created. But it also gives me a word of caution, a warning that says this is a pool with no redundancy. One device failure can cause loss of the pool. Now that's a very interesting statement, because we thought we have 2 disks in the pool. Then how is it that one of the device failure can cause the entire pool to go for a toss? For this, we have to understand the underlying architecture. We have to understand how the data is actually going to be distributed to the devices in the pool. Of course, we'll take a look at it. But before we do that, let's look at the df-h output one more time. Or maybe before that, we will list the pools that exist in here. You can see that there is a new pool by the name my pool, which is of size 2 GB. And of course, most of that space is free because we don't have data in it. So that's no surprise there. We expected it because we created a pool. Obviously, it had to be listed as a new pool in Solaris 11. Let me clear the screen and do a df-h command. And what is interesting now is that there is a pool, and that pool is automatically mounted under a mount point with the same name, which is actually /myPool. That's a very interesting behavior of ZFS file system. The moment you create a pool, you're ready to go. You don't have to worry about creating an empty directory. I mean, we didn't have a directory by the name /myPool. It was automatically created by the ZFS file system. So the moment you created a pool, it was automatically mounted under a directory, under a mount point with the same name, and it's ready to use. So I could go inside my pool. I could say df-h, the current directory. That's actually the name of the pool. I could start using this pool. Now, before we go any further, I just want to pull up a note which I have with me, specifically for the purpose of explaining the architecture in which the data gets distributed inside a pool. Now, in the diagram there, you would see a pool that is very similar to the one that we created. The only difference here is that there are 4 devices in this pool, as you can see from this command. In our case, we only added 2 devices into the pool, my pool. Barring that, there is absolutely no difference between what you see here and the command that we executed. Now, what happens as a result of this is that each of the device is going to be a part of the pool, and the data that is written to the pool is going to be striped across each of the device that exist here. To get a sense of what I'm saying, roughly take data A, B, C, D. A will be written to one disk, B will be written to the second disk, C will be written to the third disk, and D will be written to the fourth disk, which means there is absolutely no redundancy. If I lose my fourth disk here, a portion of my data is lost, which means my pool is meaningless. I've lost a good portion of my data, then what is the use of having that pool? So by default, when you add devices to a pool, the data is going to be striped across these devices. And if you have not built redundancy, if you have not kept in mind redundancy in your architecture, which is something that you don't have in this example, then obviously that is a risky affair. So it's certainly not something that you would see on a production environment. Now, we will understand how we can achieve redundancy sometime soon, but just keep in mind that when you create a pool, you added devices to it. Now those devices, the data is going to be striped across those devices that exist inside the pool. I want to tweak that statement a bit now. Probably you may not get that 100%, but as we progress with the discussion, I'm confident you're going to get 100% of what I'm going to state here. I used a statement earlier that a pool is a collection of devices. You add devices to a pool. Now I'm going to say that a pool consists of virtual devices. Now, what do you mean by a virtual device, and what is the difference between a virtual device and device? We will see soon. So if I make a statement, the data is striped across the devices that exist in the pool, maybe the more appropriate way to say that is the data is going to be striped across 4 virtual devices that exist in this case. Of course, in the example that you see on the notes here, each of this virtual device is actually a physical disk. Again, if it's confusing for you to digest what we are mentioning here, do not worry. As we take up the next example, the term virtual device is going to be crystal clear. So for now, please keep in mind, I have a pool, my pool. I added 4 devices to it, 4 virtual devices to it, and the data is going to be striped across those 4 virtual devices. Obviously, failure of one of those devices would cause the whole pool to go down, because a good portion of your data is lost if that device goes faulty. So keep in mind that you create a pool using virtual devices, and the data is going to be striped across virtual devices that exist inside the pool. Let's go back to the operating system there. Now, we spoke about a pool getting created, the pool getting mounted automatically under the name of the pool itself. Of course, you can use switches with the zpool command to change the mount point to something else. It's the default behavior. The default behavior, of course, is to mount the pool under a mount point with the name that is same as that of the name of the pool, but that behavior can be modified by using an appropriate switch with the zpool command. Everything is there now, ready to be used. What else is pending in discussion on a ZFS file system? Now, think of this as a pool that's meant for a large organization. This is where the organization's data is going to be stored, my pool. Obviously, I don't want the data of the different business units to be stored under the same mount point. I want a file system. I want separate file systems to be created for the separate business units that exist within my organization. I don't want the set of business units that I have in my organization to use the same file system. I probably would want to delegate one portion of this file system to, let's say, the engineering business unit, another portion of this file system to another department called HR, and a third portion of this file system to another department called finance. How do we do that? Now, the way we do that is by running the command ZFS create. That means create a file system. My pool is the name of the pool where I want a file system. Under that, please create a file system by the name fs1. Now, believe it or not, we are actually creating a new file system here under the pool my pool, and the name of the file system is fs1. We will do the same thing. ZFS create, I want another file system here, fs2. By the way, this is a file system for a different business unit within my organization, maybe HR. Okay, the file system is created. ZFS create my pool fs3. Maybe a third file system is created. The magic of it is, let's look at the df-h here, and you can see there are 4 file systems that are created under the my pool ZFS pool. And look at the mount point there. The mount point was inherited. The parent mount point was, of course, inherited from the name of the pool itself, which is my pool, and then it picked up the name of the file system that we used. This mount point can be changed, and that's something we would look at very soon. But the point is that now I have created 3 separate file systems under the pool, and I could give each of this file system to different business units within my organization, or I could dedicate each of this file system to different business unit within my organization. Now, an interesting thing to observe here is that, of course, for the sake of simplicity, let's do one thing. We will assign fs1 to the engineering department, fs2 to HR department, and fs3 to the finance department. So I'm going to do that by changing the mount point. Probably mount point is something that would help me represent the business unit to which the file system belongs to. So let me clear the screen. You saw the output of the df-h command. And by the way, I can use ZFS list command also to list the file systems there. So you can see this is probably a more appropriate command that you could use for the ZFS file system than the df-h command. This is more reliable than the df-h command when it comes to ZFS as a file system. So I have 3 file systems, fs1, fs2, fs3. I want to assign each of this to different business units within the organization, and for that reason I want to give it a more meaningful mount point there. Currently the mount point is /mypool fs1 /mypool fs2 /mypool fs3. ZFS is a property-centric file system. You manage it by setting and getting properties. I think a good part of the learning curve in ZFS is about learning these properties. Some properties you can set a value, some properties you can set it to off, on, etc. So as long as you know all the properties of the ZFS file system, you're probably well versed in a ZFS file system. So one of the properties that I can look at, or probably could do, is let's get all the properties of the data set called mypool. Now you can see that the mypool file system has a lot of properties. You can see a lot of properties in here. we'll take up one of the properties as an example so that you understand what it means. Let's say the mount point as a property. Now this property has a value which points to the mount point of this data set, mount point of this file system. So the file system is mounted under /mypool, and that is actually decided by a property called mount point. Now we can do the same thing for ZFS get all for mypool /fs1 as well. And if you look at the mount point properties of mypool, you can actually see mypool fs1. You can see it's mounted under /mypool /fs1. So that explains. Which means to say, if we are able to change this value to something else, the mount point of the file system is also going to be changed. So let's verify that. Before we do that, let's run the df-h command to see one more time that the mount point of each of the file system that we created is /mypool /fs1 /mypool /fs2 /mypool /fs3. I'll clear the screen and say ZFS get the property called mount point for mypool /fs1. What's the value there? The value is /mypool /fs1. I want to change that to something else. So I would say ZFS set mount point is equal to /engineering, because we wanted to give it to the engineering department, /engineering of the data set mypool /fs1. So you can see that the data set is actually nothing but a file system. Of course, I would not say that data set and file system, these are synonyms. That's not correct, but for the sake of convenience, let's consider data set as file system. We will use those terms interchangeably, at least for the sake of initial discussion, but it has distinct differences. So a data set is a file system in the ZFS. We are specifying that for the data set mypool /fs1, I want the mount point to be /eng. Let's see what happens there. Now if I get the property mount point for mypool /fs1, you can see that the mount point is changed. Of course, we can do the same thing for fs2 as well. Let's give it to the HR by specifying a mount point HR there. And for the same, we will do the same thing for fs3 as well. We will specify finance as the mount point for mypool /fs3. Now if I run the df-h command, you can see that the mount points of these three file systems that we created has changed. It's /eng for mypool /fs1 /hr for mypool /fs2 and /finance for mypool /fs3. So the default mount point was actually the name of the file system itself. When we run the ZFS create command, whatever we gave as a name there, that was used as a default mount point. But you can always change that by changing the property of the data set. And that's again a very important point I want to revisit, that ZFS is a property-centric file system. So you play around with the properties of the ZFS file system in the process of administering the ZFS file system here. So we have set the mount point of each of this file system to an appropriate directory structure. Now, by the way, the magic is that we never had a directory by the name /eng. We didn't have a directory by the name /hr. We didn't have a directory by the name /finance. All of this was created on the fly when we specified the mount point there. Now, if I look at the space that's available, each of this is sharing the pool space. The engineering mount point has 2 GB of space approximately. The HR mount point also has 2 GB of space approximately. The finance mount point also has 2 GB of space approximately. Now that's probably not good, because some naughty individual in any of this department can actually create a large file of 2 GB and everybody runs out of space. Of course, you can add more devices to it. As an example, I can always say ZPool add to the pool mypool C1T4D0. I'm adding a new device to it. That's like 1 GB of space added to the pool mypool, and that's going to be immediately reflected there. It's going to be increased by 1 GB when you add a new device into the pool there. Nevertheless, having all these file systems share the space might have its own challenges. Some of them overuse the space, and that's unfair on the other departments who uses different file systems there. So how do we restrict the space usage for each of this file system? And again, I want to go back to my old statement that says everything in a ZFS is property. You control everything in a ZFS using properties in a ZFS file system. So there has to be a property that will help us set a limit, set a constraint on the file system usage, on individual file system usage. Let's figure that out. It's actually ZFS set quota is equal to 500 MB for my pool/fs1. And by the way, remember this, my pool/fs1 is the name of the data set where or which is mounted under the mount point /eng. So we are not going to use /eng as a parameter here. You always operate on the data set. If you look at the command here, I'm setting a restriction, I'm setting a quota. The quota word I think is very clear. It's actually an upper limit, a capping of 500 MB usage for the file system fs1. So I don't specify the mount point there. I have to pass data set name as an argument in the ZFS command. So I'm saying please set a 500 MB quota limit on the data set my pool/fs1. Let's see what happens. If I run the df-h command now, you can see that the /eng mount point has only 500 MB available to be used. Now you have to be very careful in understanding this. It doesn't mean 500 MB is reserved for /eng mount point or the file system my pool/fs1. That is not the case. If you look at it, both the file systems fs2 and fs3 that are mounted under /hr and /finance respectively has 3 GB of space. They can just overuse the 3 GB of space and that's it. Engineering department does not get any space at all. So setting a quota does not mean that the space is guaranteed for that data set. That's not correct. Setting a quota only means that you have set an upper limit for that file system. It cannot overuse, it cannot go beyond 500 MB, but it doesn't get 500 MB guaranteed. So the question now is there a way we can guarantee the 500 MB of space, or let's say 400 MB of space or something, For that, again, it's a property based file system, so there has to be some property in the data set that controls this behavior, and the property is ZFS set reservation is equal to 400 MB for my pool/fs1. Again, we are operating on the data set and not the mount point. Remember, my pool/fs1 is mounted under the mount point /eng. Now what I'm doing is my pool/fs1, I'm setting a reservation of 400 MB, meaning 400 MB has to be reserved for my pool/fs1. But there is a quota. It cannot go beyond 500. So 400 MB is guaranteed for the file system mounted under /eng, whereas it cannot go beyond 500 MB. That's what is set by the quota there. Let me run this command. I can always run the get command to find out what is the value of reservation at any given point in time. You can see that it's 400 MB in size. Of course, I run the df-h command. I can see that the space that is available now for the file systems fs2 and fs3 has reduced. 400 MB has been taken away from these file systems. Why? Because 400 MB is guaranteed for the engineering department. So looking at the df-h output, you probably don't get a full picture there, because one of it says, the size is 2.9 GB, but the available is 2.5 GB. The other guy has available 500 MB. So you would have to play around with these reservations and quota properties to understand the exact distribution of the space for each of the file system that exists inside a pool. But I hope you get the idea, the difference between the reservation and the quota there. So far we looked at 3 important properties of the file system. One is the mount point, which is where the file system is mounted. The second is the reservation and the quota. Second and third, which is basically quota is the upper limit that you want to give for a specific file system, whereas reservation is a guaranteed space that you want to give for a file system. So these are the 3 properties that we have learned so far. Now, if I want to get some idea about the devices that exist in my pool, which is my pool, I can always say ZPool status my pool. Now this will show me that there are 3 devices inside my pool, and I can see that these 3 devices are not redundant because it's just 3 virtual devices that exist inside the pool called my pool. So the question now is, if this is not a configuration that is supported in production environment, how do I build a ZFS pool that is supported in production, or that offers some level of redundancy for the data there? To understand that, I am actually going to destroy the pool. ZPool destroy my pool. So the pool is destroyed. ZPool list. Oh, by the way, please do not casually run that command. Certainly you are destroying the pool. There are ways to recover it, but it's not something that you would casually run in a production environment. For me, as you know, I'm playing around with the 6 disks. There are experimental disks, there are virtual disks that exist on my virtual machine, so I can do whatever I want. It doesn't give you the liberty to do that on a production box, of course. What I will do now is to create a new pool. ZFPool create my pool again, or maybe use a different name, pool 1. Okay. This time around, I'm not going to mention the name of the devices one after the other. I'm actually going to say mirror C1 T1 D0. I think it's C1 T2 D0 and C1 T3 D0. And I would also say mirror C1 T4 D0 and C1 T5 D0. Of course, I have 6 additional disks on my system. So I'm creating a pool by the name pool 1. I think that part is self-explanatory. I'm creating a pool by the name pool 1, and I'm creating a mirror using 2 disks, C1 T2 D0, C1 T3 D0, and I'm creating another mirror which is C1 T4 D0 and C1 T5 D0. Let's not worry about what might have happened or what is the exact pool that gets created here. Let's create the pool. The good news is that this time around, no warning messages, no word of caution, nothing. I mean, it just created a pool. So that means I did something right here. Probably this is a pool that offers some redundancy, so I can use this on a production system. As before, we will list the pool, and you can see the pool 1 listed as a part of the pool. We can also look at ZPool status pool 1 to find out. Now, interesting, I have mirror 0 and mirror 1 here. To understand it better, maybe I'll go back to the notes there and pull up something similar to this. Now, what we did just now is exactly what you get to see in the diagram here. I created a pool. Of course, the name of the pool in this example is my pool, but we created something like a pool 1. And you can see the keyword mirror here, followed by that are 2 disks, and then another keyword mirror here, followed by that 2 disks. What happened is that I got a pool by the name pool 1 in my example with 2 virtual devices. Now this is where I want to emphasize the word virtual devices again. 2 virtual devices. One virtual device that is a mirror of 2 disks, and another virtual device that is a mirror of another 2 disks. So there is this one mirror here, which is a virtual device. There is another mirror here, which is a virtual device. Now imagine how the data is going to be written to this. I have A and B. A will go to this virtual device. Remember that the data is going to be striped across the virtual device that exists in the pool. That's exactly the statement we made some time back. It's going to be striped across the virtual device that exists. In our earlier example, there was no mirror. It was all 4 virtual devices. And the data was striped across all the 4 virtual devices. One device fails, the data is lost. Here I have a mirror as a virtual device, another mirror as a second virtual device, and what happens as a result of that is the data A that is written to one virtual device has a copy, and data B, the second stripe unit, has a copy of it in the mirror. So something goes wrong to one of these disks wouldn't really affect the pool. I still have a copy of A in another disk in the mirror. I still have a copy of B in another disk in the mirror. So if ever you want to have a redundant pool, you would possibly use a mirror pool. Of course, there are other possibilities like RAID Z, for example. That's an improved version of RAID 5 in a ZFS, where you need minimum 3 disks to build a pool. You have data and parity written to the third disk, so in case if one of the disk fails, you can actually recover the data, or you can use the other 2 disks to retrieve the data. So if you are looking for a redundant ZFS pool, there are 2 options for you. One is a mirror, the second is RAID Z. RAID Z has again 3 varieties of it. You want 1 parity, it's called RAID Z1. You want 2 parities, it's RAID Z2. You want 3 parities, it's RAID Z3. Now don't worry too much about RAID Z for the time being. So I have a mirror pool here. Now the redundancy is guaranteed. Have a look at this picture here. I think of this as mirror-0. I think of this as mirror-1. The data in the mirror-0 is one portion. The data is mirror-1 is another portion. So if I'm writing A and B, for example, A will go here. There is a copy of A that's going to be here. B will go to the virtual device, which is the mirror-1. B will have a copy in the subdisk of the mirror-1. So if I go back to my mirror here, this is the command output representation of the diagram that we observed. So this will have same data. These 2 disks will have the same data, A dash, and these 2 disks would have the same data, that's like B dash. The data is going to be striped across mirror-0 and mirror-1, which is what you observed in the diagram there. So always use a mirror pool or a RAID Z pool, RAID Z2 pool, or RAID Z3 pool. Let me destroy this. ZFS destroy pool 1, and just for the sake of completion, let me show you how you can create a RAID Z pool. Z pool create pool 1 RAID Z, which actually means RAID Z1. That means 1 parity, which means you need minimum 3 disks. Of course, if you are building RAID Z2, you will use a keyword RAID Z2, but you need minimum 5 disks so that 2 parity, 2 disks can be used for generating parity for the data there. RAID Z2, sorry, I will use RAID Z here, C1 T2 D0, C1 T3 D0, C1 T4 D0. And now if I look at the Z pool status, pool 1, I can see that it's actually a RAID Z volume. Now oftentimes, you will be tempted to have a RAID Z here and then followed by that mirror. That's not recommended. As long as far as possible, make sure that a pool has the same configuration. You have a mirror, etc. in the pool, rather than having a mirror and RAID Z coexisting in a pool. So now that we have understood the RAID Z also, let's go inside. By the way, we lost all the file systems that we created because we destroyed the pool. Let's destroy the pool again. Destroy pool 1, and we'll go back to the original pool. Z pool create my pool mirror C1 T2 D0, C1 T3 D0, mirror C1 T4 D0, C1 T5 D0. We can verify that as a pool status my pool, and you get to see that there are 2 submirrors to it. As before, we can see it's automatically mounted, and maybe we create a file system below that. ZFS create my pool /fs1, ZFS create my pool /fs2. Only 2 file systems are required, and you remember some of the properties we looked at, like setting the mount point. If you look at the df-h output, it's picked up the default mount point, which is /mypool /fs1 /mypool /fs2. So let's set a mount point. Mount point is equal to /eng for mypool /fs1. ZFS set mount point is equal to /hr mypool /fs1. Again, if you look at the df-h, both I guess okay, I made a mistake here. Let's set it to eng, and for the fs2 let's set it to hr, and df-h will verify it's actually /eng and /hr. Again, each of them is sharing the pool, so one of the file system consumer, one of the file systems consumer can actually take up the full space, and that's going to be unfair to the consumers of the other file systems. If you want to restrict the usage of a file system, you can do that by using properties like quota, and you can reserve space for a file system by setting a property called reservation. We can actually do that as ZFS set reservation is equal to 750 MB for my pool slash fs1, but I want to make sure that it doesn't use more than 1 GB of space. So if I look at the df-h, you can see that the space available for the ENG is 1 GB because that's what we set as a quota. But since we specified 750 GB as reserved space for the ENG file system, you can see that space is taken away from the other file systems that exist under the same pool slash my pool. So I hope those three properties are understood clearly. Now let's go inside slash ENG. df-h dot will show you where you are. Let's create some files: touch f1, f2, f3, f4, f5, f6, f7, f8, f9, f10. So we have some files inside this. Let's also create a large file, mk file 100M large file. Let's create a large file inside the file system my pool slash fs1. So again, list the files under this. You can see there are number of files plus a large file under the my pool slash fs1 file system. Now what am I going to do with this? One of the interesting features of ZFS file system is its ability to take snapshot. Now let's take a look at this. I think it's very clear to us that the size of the large file is 100 MB because that's what we created, isn't it? It's 100 MB in size. The large file is 100 MB in size. The ZFS list command will show you that, let's find out where is ENG. Yeah, it says, used is 100 MB because F1 to F10, the files we created using the touch command, it doesn't consume any space. That's negligible there. But what consumes space in this is the 100 MB file that we created using the mk file command. So that's 100 MB in size. Now what we will do is use a magical feature of a ZFS called snapshot to take a snapshot of this file system. Let's take a snapshot of this file system. The ZFS snapshot of which file system? Of my pool slash fs1. And then use a format at to specify a string that by and large would help us understand why, when, how we took this snapshot. For example, if I'm taking this snapshot on Friday, I could actually specify Friday here. So what this indicates to me is that this is a snapshot of a file system called my pool slash fs1, and this string is likely to help me understand why, when, how this snapshot was taken, so that later if I want to restore the snapshot back, I kind of get an idea of when, why, how this snapshot was taken. So let's take a snapshot of this file system. It's done. That was super fast. Now what has happened here? Let's find out what just happened. Okay. If I go to the ENG mount point, which is the mount point for the my pool slash fs1, I hope this syntax is understood clearly. I'm taking an ZFS snapshot of file system my pool slash fs1, and then I give a name, a description that lets me identify why, when the snapshot was taken, etc. Now remember, this large file is 100 MB in size. I can list a snapshot by using the ZFS list command. By the way, if I just run the ZFS list command, it lists only the file systems. And one of the file system that is of interest to us is my pool slash fs1. We looked at the 100 MB space that it is using because of the 100 MB large file that we created. But nowhere in the output we are able to see a snapshot. Of course, snapshot also is expected to consume some space, isn't it? I mean, it has to be listed as a part of the ZFS list command. Starting from a specific release of Solaris operating system, ZFS list command no longer show you the snapshots by default. I should specify ZFS list -t snapshot to list the snapshots. And when I do that, I get to see a snapshot that I just created, which is actually my pool / FS1 at Friday. Interestingly, the amount of space that it used is 100 MB in size. I mean, it's 0. It's actually 0. And there is something that says, it's referring 100 MB of space. That's not of any interest to me for the time being. But what is interesting to me here is that the snapshot, when it is taken, it initially takes no space at all. As long as the file system and the snapshot are the same, it consumes no space. And that's exactly the principle in the ZFS as a root file system as well. When you perform the BEADM create command, you observed that the new boot environment that is created consumes negligible amount of space thanks to the snapshot facility of the ZFS file system there. It consumes 0 amount of space. Of course, snapshot will start consuming more and more of the disk space, and that depends on the amount of changes that happen to the original file system. Now let's take that example there. I go to the ENG and I say, okay, let me remove the large file. Now that's a modification to the actual file system. From the actual file system, I have removed a 100 MB file. Now, your snapshot of this file system is no longer referring to the data block of the original file. On the other hand, the 100 MB file that used to exist in this file system, which is with the snapshot now, is fully and wholly owned by the snapshot. Now, how do we know that? We run the ZFS list -t snapshot command, and now you can see that the file system the snapshot is actually consuming 100 MB of space. Why is that? Because this 100 MB file now belongs to the snapshot. It is not referring to the 100 MB file that exists in the file system, because the original file system no longer has a 100 MB file in it. So I removed that file. Now the 100 MB file is solely and wholly owned by the snapshot there. How do I roll back? Let's go to the engineering department and look at it. Okay, now I don't see the large file, but I can say ZFS roll back from the snapshot my pool / FS1 at Friday, and I look at it. You can see that the large file has come back. And now if I run ZFS list -t snapshot as an example, I can see that the space used is negligible again, because now the snapshot my pool / FS1 at Friday is actually referring to the original file that exists in the actual file system. I hope you kind of get an idea of why snapshot does not consume space to start with, because it is referring to the data blocks in the original file system. But as and when the data is modified in the original file system, you would start seeing space consumption by these snapshots here. So snapshot is a wonderful feature. You probably might be curious to know where this snapshot is located. Now, before I say that, I want to make it very clear that snapshot is not an alternate way of backing up your data. Snapshot resides in the file system, so a disk failure, everything is gone. Your file system is gone, your snapshot is gone. Of course, you can use the snapshot to send the data to somewhere else, but don't think of snapshot alone as a backup solution there. It's not meant for a disaster recovery, because your hard disk failure, you lose your file system, you use your snapshot. Now, where is the snapshot located? Like I mentioned, it's located inside the file system. That's where I am. I am inside the file system there. Let me look at the ls command and see where the snapshot is. Well, I don't see any snapshot in here. So where might my snapshot be? I do an ls -a command. I don't see any additional files. I see F1, F2, F3, F4, all that I saw without the -a option itself. But interestingly, if I use .zfs, I can see that I was able to navigate to a directory called .zfs. It was not displayed even with the -a switch there. Even though dot indicates a hidden file, ideally it would have been displayed when I used the -a switch with the ls command. That was not the case, so .zfs was not displayed to me. Under that you have a directory called snapshot. Under that you have Friday, and that's where the snapshot is. Of course, the snapshot is a read-only copy. Any attempt to modify the snapshot is not going to work. So I'm not able to modify the snapshot at all. By the way, why was the .zfs directory not visible to me even with the ls-a option. Again, I want to go back to my previous statement that said everything in a ZFS is actually a property. There might be a property, ZFS get snapdir for my pool /fs1. You can see that the snapdir property for this file system. Remember, my pool /fs1 is mounted on /eng, so that's hidden. If I set the property ZFS set snapdir is equal to visible and say my pool /fs1, I say ls-a, I'm able to see the .zfs directory there. So it's been made hidden because what happened was that if it was made visible, some of these backup tools started picking up data from inside the directory as well. So to avoid that from happening, this particular directory was made hidden by default in one of the specific releases of Solaris operating system. But you can always control that by using the property snapdir. So I think that again reiterates a very important point that ZFS is a property-centric file system, and you control the behavior of the ZFS file system by modifying the values of these properties that exist. So now we understood the mount point property of ZFS, we understood the quota property of the ZFS, we understood the reservation property of the ZFS, we understood the snapshot, how we take a snapshot, why doesn't the snapshot consume a space to start with, where the snapshot is located, how we can view the snapshot. All of those details I hope is understood. Now df shares is a command that can be used to list the file systems that are shared, NFS, network file sharing. And if you remember, traditionally you had to edit a file called etc dfs tab and put an entry in the etc dfs tab for the file systems that you wanted to share with the outside world. So if you wanted to share a file system in the network, you generally put that entry in the etc dfs tab. Again, that's going to be controlled by some properties in a ZFS. If I look at ZFS get share.nfs for my pool /fs1, you can actually see that it's off, which means it's not shared. All I need to do is to say ZFS set share.nfs is equal to on for the my pool /fs1. And now if I say df shares, you can see that the file system is shared. Of course, there are other parameters you can pass in this ZFS set share nfs command to control the permissions on these file systems. But as you can see, sharing a file system in Solaris 11 is just with one command. You don't have to worry about the etc dfs tab or any of those files that you might have fiddled around while configuring NFS in the previous versions of Solaris using different file systems. So that's another property you might want to keep in mind, sharing a file system by using share.nfs command. We talked about snapshot as a read-only copy of the file system. What if you wanted a read-write copy of the file system? Imagine a situation where I want to create an exact same copy of a file system, but I also want a read-write capability for that. The way I do that is first by creating a snapshot, of course. Or before I do that, I wanted to show you something else as well. I go to the ENG mount point there, and let's create a new file, touch F11. So I created a new file. Let's remove a file and let's modify a file. Let's say this is a test file. And now I'm going to take another snapshot, which is by using the command ZFS snapshot my pool /fs1 at Friday 2. Maybe a second file, a second snapshot there. So remember, there are two snapshots for this file system. Now, how do I verify that? It's ZFS list -t snapshot. There are two snapshots for this file system. One is my pool /fs1 at Friday. The second one is my pool /fs1 at Friday 2. Between the first and the second snapshots, some changes occurred in the file system. A file was modified, a file was removed, a file was created. There's a cool command introduced in Solaris 11 called ZFS diff my pool /fs1 at Friday, my pool /fs1 at Friday 2. Now that's cool because it gives me the differences between the snapshot number 1 and the snapshot number 2. It says, the first line says, of course the file system was modified. Now what was the modification? The file M1 has been deleted. That's indicated by the minus sign. File F2 was modified. That's indicated by the M sign. And a new file has been added, which is F11 and indicated by the plus sign there. So this is a cool command introduced in Solaris 11 to identify the differences between two snapshots that you've created for a specific file system. Just wanted to show you before I forget. Now what I want really is a writable copy of a file system. I have the data here. Maybe let me add a data. This is a test document. This is used to test the clone facility in ZFS. And I do a control D. I have a letter in my file system /eng. What I want to do is I would create a clone. Okay, and the clone I create is from the snapshot mypool /fs1 at Friday 2. And then I would specify the name of this is fs3, or fs3. Let's put it as fs3. Now please keep in mind one thing, that a clone of a file system can only be created from its snapshot. So you have to have a snapshot first of that file system to create a clone. What do we have? If I do a df-h, obviously the file system is mounted under the default mount point, which is /mypool /fs3. So I go to /mypool /fs3 and I do an ls. I can see the same set of files that existed in the file system there, eng. Of course, one blunder I made was letter.txt, which we added, was of course not a part of the snapshot that we created. We could have created a new snapshot before creating a clone. That didn't happen, so obviously you don't have that letter.txt inside this directory. Never mind, I mean, doesn't really matter. So we have all the files that exist in fs1 also exist in fs3, and the important part is that I can actually do a touch command and say f9. Let's say touch new file, for example. So I'm able to create a new file in the clone, and that's exactly the difference between a snapshot and a clone. A snapshot was a read-only copy. We were not able to create a new file inside a snapshot, whereas a clone that you created from the snapshot of a file system is a writable copy. So you can modify the file system, and this is very useful if you really want to take a snapshot of a file system and apply something on that file system and see how it behaves, and later apply that to the original file system. So I was able to do this. Now the catch here is that this clone is dependent on the snapshot, who in turn is dependent on the original file system. So as long as this clone exists, I cannot delete the original file system. I can actually try deleting it. I would say ZFS destroy mypool /fs1. It says, I'm sorry, I cannot destroy it because it has child data sets there. So think of mypool /fs1 as the parent file system, whereas the mypool /fs3 as a child file system. It's a clone of the fs1 there. I want you to closely look at one of the properties here. If I go to ZFS get and specify all and say mypool /fs3, I want to list all the properties of fs3. One of the important property that I want you to pay attention to at this in the context of the cloning and snapshot is this. Let's go and find out the property here. Origin. Now this is a property that you might want to pay attention to. We are looking at the property of, maybe we'll clear the screen and just get the property, specific property called origin of mypool /fs3. Now what this tells us is that this mypool/fs3 is actually originated from the snapshot, or in other words, it has a dependency on the snapshot, it has a dependency on the original file system. Now, at any point in time, if you feel you want to take this out, you want this file system to be promoted as the original file system, let me also show you one more thing. Let's go to mypool/fs1. It doesn't have a property. fs1, remember, is the original file system. You created a snapshot from fs1, and from that snapshot you created fs3. So fs3 has a dependency on the snapshot of the fs1, but you decide at a later stage, fs3 is going to be my actual file system. I don't want fs1 anymore. I made a lot of changes in fs3. That is why I cloned fs3. Now I want to use that as my original file system. All I need to do is run the command ZFS promote mypool/fs3. Now this becomes the original file system. Now fs1 file system has no dependency on this. fs1 file system is not the parent file system of fs3. You can go ahead and delete that. But what is interest to us is the origin property again. If we go back to the origin property of fs3, you can see the value is gone, meaning it's no longer dependent on that snapshot there. I do is ZFS get origin mypool/fs1. This has a dependency on the snapshot. Look at the name of the snapshot now. The snapshot is actually renamed as mypool/fs3 at Friday 2 rather than mypool/fs1 at Friday 2. So literally what you've done is you've promoted the clone to be the actual file system now. You made probably some changes on that clone and you wanted that to be the actual file system, and then take away the original file system from the picture, and this is the way you do it. So we have discussed about pool, we have discussed about non-redundant pool, we have discussed about redundant pool like mirror, raids, and etc. We discussed about different properties of ZFS file system like mountpoint, quota, reservation, share nfs, snapdir, the origin, as you can see here. We looked at the command to take a snapshot, rolling back to a snapshot. We looked at the command to create a clone, and promoting a clone as an actual file system. So these are some of the commands you might want to keep in mind starting to play around the ZFS file system there. One another command that is probably handy for you is the ZFS snapshot, like I mentioned, is not a backup solution. It takes a snapshot under the same file system. So if the file system gets corrupted or the disk goes faulty, then obviously you lose the snapshot also. So what you generally do is save the snapshot to a file or send the snapshot to a different box. So when you do that, it's not just the snapshot, but the file system along with it would also be sent to a file or would also be sent to a different box. How do we do that? It's ZFS send command, mypool/fs3 at Friday 2, and then you specify the name of the file, which is, let's say, TMP backup. Of course, interestingly, this file location can be an nfs.share. Usually when you take a backup of your root file system, you run the same command of the root file system for the root ZFS snapshot, and then you send it to an nfs.share, which is, it's actually very critical to have this file stored in a nfs.share or something if you want to recover a root file system failure. There is a separate episode in the playlist which does that, but what I'm doing here is I'm sending the snapshot along with the file system to a file called TMP backup. Now let's look at the file command and see what TMP backup has. It's a snapshot stream, pu-sh TMP backup. That's like 100 MB because of the large file there. If I go inside mypool/fs3 and look at the files, it's there. What I'll do now is ZFS destroy mypool/fs3. Obviously, of course, I can actually say -r to destroy. Sorry, it's in the wrong place. Let me destroy this by using the -r command. ZFS destroy That's the wrong option there, -R, and last time, yes, it's gone. So my pool /fs3 is gone. I go inside my pool /fs3. There is no such file or directory. Now what do? I of course have a backup of the data taken. I can say ZFS receive to the my pool from the file backup. Alright, I need to specify the name of the file system here, which is fs3, let's say, for example. And now if I go to /mypool/fs3, I have all the files back. So ZFS Snapshot is certainly not a backup solution because it resides in the file system. But you can always use the ZFS send command to send the snapshot to a file. That file could be a file residing in an nfs.share. And later you can use the ZFS receive command to retrieve those file systems and the snapshot. The good news here is that if I look at the ZFS list -t snapshot command, I would be able to see even the snapshot that was created for the fs3 file system. So the send command sends not just the snapshot but also the file system. Ideally what you do is you say ZFS send mypool/fs3 at Friday2, and then you pipe it to an SSH command on, let's say, a host, host2. I don't have it, I'm just showing you the syntax of the command, and I can say ZFS receive mypool. So what it does is it basically, by the way, sometimes you don't have the permission to run the command, so you can use the pfexec there. So what this command actually does is it will send the pool. Instead of sending it to a file which we just observed, it sends the snapshot to a remote machine, in this case host2, and there the ZFS command will receive that to a new pool called mypool. This is a very handy tool to migrate ZFS file system from one machine to another machine. A very, very handy tool there. Lastly, I'm going to do something very destructive. Let's say zpool list command to list all the pools that currently exist in our system. So we have our pool, which is a root pool. We have my pool and my pool 2. I'm going to do something nasty by running the command zpool destroy my pool. I wouldn't expect anyone to do this on a production box with a lot of pools and file systems and sensitive data in it, but this is just a demo. What if you accidentally destroy a pool? Of course, it's gone from the list here. There is no longer my pool in the list. What we could do in a situation like this is to run a command zpool import -d, which will show me the pools that are destroyed. So I can see that there is a pool that was destroyed, my pool, and I can attempt to recover it. I can say zpool import -d my pool, and I can say zpool list command, my pool is back. I can say my pool/fs3, my data is also intact. So in this quick segment, I mean, we had to run through a number of commands around ZFS very, very quickly, and I hope this has given the foundation around the ZFS file system in Solaris 11. There is a lot of reading and practice that you need to do to master the ZFS file system. I mean, you can spend many number of days playing around with the ZFS file system with the options that it has for the two commands that we discussed, which is zpool and ZFS. But I really hope a few minutes that we had, we were able to discuss some of the important concepts around ZFS, some of the important commands around the ZFS file system, like creating a pool, adding devices to it, redundant pool, non-redundant pool, properties of these ZFS file systems like quota, reservation, nfs, mountpoint, snapdir, etc. We understood how to take a snapshot. We know snapshot resides in the file system. We also know snapshot does not consume space to start with. We know how to roll back a snapshot. We know how to create a clone from the snapshot. We know how to promote a clone. And we also know what happens to that origin property when we promote the clone to the actual file system. We understood how we can find out the differences between two snapshots, and finally we also understood how we can split a mirror pool and in the last command we destroyed a pool. We were able to bring that pool back by using the import -d option. So these are the basics of the ZFS file system. To help you get started with the ZFS file system, there are enough literature available in the form of product documentation and blogs and demonstrations on the internet, which I hope you would make use of to learn ZFS in depth. Once again, thank you so much for spending time watching this video.